Hi, my name is Christelle Sabatier. I teach neurobiology at Santa Clara University. In this tutorial, we're going to discuss the mechanisms by which neurons transmit information through the body. Specifically, we'll be discussing the movement of ions across the membrane of neurons, referred to as membrane potentials and action potentials. Throughout the video, we'll be applying those concepts to the principle illustrated here, that of pain sensation. Pain neurons can sense pain information or stimuli applied to different parts of the body, in this case, the hand. However, they are specific to the types of stimuli that they respond to. And so in this case, the feather applied to the hand does not result in pain information being transmitted through the nervous system, whereas enough force being applied with a needle does result in pain information. By the end of the tutorial, you should be able to explain why that is at the level of membrane potentials and action potentials. Now that we've established the context for neuronal communication that we'll be using throughout the tutorial, let's go through what you can expect. First, we'll discuss what happens at the neuronal membrane at rest. What are the ions that are relevant to setting the membrane potential, and how does they set up the charge gradient that is critical to information processing by the neurons. Then we'll go into the initiation and propagation of action potentials down axons, and roughly what happens when those action potentials reach a synapse. The action potentials that we'll be discussing in this tutorial could take place in all sorts of different neurons throughout the nervous system. However, we will focus on a sensory neuron responsible for the sensation of painful stimuli. Now imagine that you are perceiving some kind of painful stimulus, like a very hot temperature, by your hand. This information is sensed by the neuron's projections all the way out to the periphery and has to be transmitted all the way to the cell body of that neuron located near the spinal cord. If we look at the spinal cord in cross-section, as is shown here, the cell body of that neuron, sensory neuron, would be located in the specialized ganglia just outside the spinal cord. The projection that we were discussing going all the way to the hand is located here, and there's an additional projection going centrally into the spinal cord to make synapses onto other neurons that might be responsible for eliciting a response to the painful stimulus. This neuron here is a diagram of that sensory neuron that we've been discussing. Now, the action potential needs to be initiated from where the stimulus is sensed, in this case, something painful, and transmitted all the way down those projections to the synapse. So let's zoom in and look at the molecules that are responsible for doing this job. So let's zoom in even closer to the axonal membrane of these neurons. At rest, that is when they are not receiving any stimuli at the dendrites, these neurons look like this. And we're going to focus in on just a few of the membrane channels that are relevant to membrane potentials and action potentials, namely the potassium lead channels, the voltage-gated potassium channels, and the voltage-gated sodium channels. At rest, because of the work of the sodium-potassium pump, which is not pictured here, these neurons have a high concentration of sodium outside the cell relative to inside, and a high concentration of potassium inside the cell relative to outside. The cells at rest do not have a an easy path for sodium ions to move across the membrane. However, potassium ions are free to move through these potassium leak channels. And so they will find their electrochemical equilibrium, whereby the charge differential across the membrane offsets the concentration differential. This results in a more negative charge inside the cell compared to the outside the cell. This is referred to as the negative membrane potential. And often we think about neurons at rest at sitting at around negative 70 millivolts. When a high pressure stimulus, for example, is sensed by this pain sensing neuron, the dendrites open up some specialized mechanically gated channels which will allow some sodium ions to flow into the cell. This will bring positive charge into the cell and depolarize the membrane. The membrane potential becomes more positive as a result of that. If this stimulus is sufficient to activate the neuron, it will depolarize the membrane to a threshold voltage that allows the voltage-gated sodium channels to open up. Once that happens in the axon, the sodium rushes into the cell, further depolarizing the membrane. This depolarization is the initiation of an action potential. Voltage-gated sodium channels have some interesting properties, however. Very quickly after they open, a specialized inactivation gate that's on the inside of the cell will swing closed and inactivate the voltage-gated sodium channel, thus blocking further flow of sodium into the cell. At the same time, because the cell has become so depolarized, voltage-gated potassium channels are triggered to open. Potassium now is allowed to flow out of the cell down its electrochemical gradient, thus resetting the membrane potential back towards rest. Note that throughout this process, the potassium leak channels in gray here remain exactly the same, simply responding to the types of membrane potentials that are changing as the action potential is moving through, but not in itself opening or closing. They stay open. Because voltage-gated sodium and potassium channels line the entire length of an axon, the action potential propagates by sequential opening of voltage-gated sodium channels, thus propagating the action potentials toward the synapse. At the synapse, a change needs to take place from the movement of information as an electrical signal to movement of information as a chemical signal, namely the release of neurotransmitter. This takes place due to the presence of voltage-gated calcium channels that exist very specifically at the synaptic terminus. These channels are triggered to open due to the depolarization caused by the opening of voltage-gated sodium channels. Once calcium flows into the cell, it will trigger the fusion of synaptic vesicles and the release of neurotransmitter. This will be discussed in another tutorial. So let's put this all together in the context of the pain sensation circuit that we discussed at the beginning of this tutorial. A pain neuron has its dendrites on the hand and is sensitive to pressure information. a feather brushing the hand is not enough pressure to trigger the pain sensing neuron to go past its threshold. A little bit of sodium may flow in, but it's not enough to depolarize the cell to the extent to open voltage-gated sodium channels. As a result, the sensing of the feather on the periphery of the body does not lead to painful information being sent through the circuit. And the little bit of sodium that flows into the cell, called the graded potential, will quickly dissipate with time and distance, never triggering an action potential. This is very different in the situation where a large amount of pressure is applied through a needle. In that case, the pressure results in a large influx of sodium, which is enough to get the voltage-gated sodium channels past threshold. They all open at that moment, further depolarizing the cell, initiating an action potential, which will then, as it propagates, lead to subsequent opening of voltage-gated sodium channels throughout the axon towards the synapse. As a result of the inactivation of voltage-gated sodium channels and the opening of voltage-gated potassium channels, the membrane potential of the axonal parts that have experienced the action potential will reset back to rest, ready to sense a new stimulus or continued applied stimulus.